So it's finally time to do some fun stuff. We're going to do some drawings. And we're going to do Lewis dot diagrams, which we learned how to do last unit for atoms, single atoms of a given element. Now we're going to do Lewis dot diagrams for compounds. And we're going to start with ionic compounds. We said when we learned how to do these initially, the great thing about Lewis dot diagrams is that they give us a picture of the atom. And now they're going to give us a picture of the compound. The other great thing as we move into compounds is the Lewis diagram shows us the possible arrangement of the atoms within the compound. In other words, how the atoms might be aligned with regard to one another, sort of a preview as to what we think the overall shape of the compound might be. And obviously we said with ionic compounds we have a transfer or donation of electrons from metal to nonmetal, metal to polyatomic ion, any of the given scenarios. What we're going to focus on the Lewis diagrams for an ionic compound between a metal and a nonmetal. And we're going to start with our old friend table salt, NaCl. And we're actually going to skip this second step. So don't worry about this. We're going to combine that all into the first step. The first thing we do when we're drawing the Lewis diagram for a compound, for an ionic compound, we're going to draw the Lewis structure for the metal. And I'm using an X for the metal's electron just to show you the difference between and keep track of which electrons belong to which atom. Next, we do the Lewis diagram for chlorine, 4, 5, 6, and 7 valence electrons. So we have them side by side. And one of the tricks here, you want to try to keep the unpaired valence electrons in between the atoms that are bonding. It just helps. It makes it a little bit easier. So, like we said, there's a transfer of electrons from the metal to the nonmetal. So we're going to draw an arrow showing the electron leaving sodium and attaching to chlorine and forming a chloride ion. So we're going to skip over step 2. Now we're going to redraw this as the ionic compound after the transfer has been made. And one of the things with ionic compounds is we need brackets and charges. Put the and in here. So we're going to draw sodium with its old valence shell. It only had one valence electron and it lost it, so it now has 0 valence electrons in that original shell. And it has a charge of +1 because it lost that one electron. Right next to it, we're going to draw chlorine with its valence electrons, the 7 it had initially, and the 8th from sodium. Close its bracket and give it its negative charge. So now you see the Lewis diagram for an ionic compound illustrates that a transfer of electrons have been made, and you have to use brackets and charges or you're not going to get full credit on the exam. This is just how it's illustrated so that we know we have ions and not atoms, and it's an ionic compound, not covalent. Let's take a look at a couple more examples. Very similar to the one we just did. We start with potassium, give it 1 valence electron. Right next to it, we're going to draw fluorine with 1, 2, 3, 4, 5, 6, and 7. We show the transfer of electrons from potassium to fluorine. And now it's time to draw them post-transfer. Potassium with bracket and charge. Chlorine. With its extra valence electron. Bracket, oops, and that's fluorine. Got caught up in my last example. Fluorine, not chlorine. And now you have potassium fluoride. The example below that, barium sulfide. We'll learn how to name these later. Barium, if you look it up on the periodic table, is in group 2. So barium has 2 valence electrons. Sulfur is group 16, which means it has 6. We illustrate the transfer. 1 electron snaps here, 1 electron snaps in down there. And now we draw the compound post-transfer. Since barium has lost 2 electrons, it has a plus 2 charge. Since sulfur has gained 2 electrons, it has a minus 2 charge. And then our last example is a little more difficult, a little more involved, and I'm going to show you a shortcut, a trick to condensing this thing. We start out with our aluminum, right here in the middle, and draw a little smaller because this one gets bulky. We have 1, 2, and 3 valence electrons. We've got a bromine up top. 1, 2, 3, 4, 5, 6, 7. A bromine I'll put out here in the middle. 1, 2, 3, 4, 5, 6, 7. And a bromine down below. 1, 2, 3, 4, 5, 6, and 7. I'm going to remind myself to make these boxes a little bigger for next year. So now we're going to transfer 1 electron up here, 1 electron over here, and 1 electron down here. The aluminum loses a single electron to each of the 3 bromines to make 3 bromide ions. Now, instead of drawing the whole thing really bulky and putting a bromine here, a bromine here, and a bromine here, what we can do is condense this using a coefficient. And we can say aluminum, which has lost 3 electrons, so it's now plus 3. And there are 1, 2, 3 bromines, so we can put a 3 out in front. Put our bromines with their bonus electron and a minus. Now, it's very important to understand. You can put a coefficient here. But one thing that you can't do, it's a common mistake that people make, is to say Br and then put the 3 here. Using a subscript instead of a coefficient is wrong. This indicates here that you have a bromide attached to another bromide attached to another bromide. That would be 3 negative ions bonding to one another, and that doesn't happen. Okay, so it's not 3 bromides attached to one another. It's actually 3 bromides attached to that guy.